I want to talk about multidimensional scaling. The classic problem in multidimensional scaling is this. Have you ever seen a map? And on the bottom of the map, they often have a pairwise table of cities. So you have Los Angeles, New York. Of course, Fayetteville will be on there. Let's see, Miami, it's another big city, Seattle, and Denver, sure, good enough. Pretty much these are the cities you'll see in a table, and there will also be, and you'll see a table that basically shows the distances between all of the cities. So the distance between LA and LA is probably 0, right? Because if you're in LA, then you're in LA. Distance to New York is, I should put more space between all of these things. Anybody have any idea? Let's go with
pretty close to
2,142.3 ish. I totally made that up. I have no idea. LA to Fayetteville is probably 1532. I don't know. To Miami is going to be 22, and Seattle is going to be what, 944 miles, and to Denver it's going to be 933, something like that, right? Now you could imagine we filled out this whole table, and they usually use a upper triangular map or a lower triangle. They usually do a triangle rather than a full matrix. Why? Because why? I mean, obviously there's no point in telling you the distance between Fayetteville and Fayetteville. It's always going to be 0. And if you know Fayetteville to New York, you can also find New York to Fayetteville by going backwards. So it's a mirror image type matrix, and there's always going to be zeros down the diagonal, and they don't want to repeat that. So they usually have a upper or lower triangular matrix. Now, a problem we could ask is, hey, now that we know the distances to all these cities, imagine you didn't have a map that goes along with it. Imagine that only this piece of the map had been ripped off for some reason, and you wanted to reproduce the map. Could you do it? And this is kind of one of those programming challenge type questions we love to ask at job interviews and things like that, isn't it? Because, here, you've got a bunch of data. Now place the cities where they go approximately. Can you pull it off? This is the problem that is solved by multidimensional scaling, and here's how one would do it. Now, by the way, there are a few different ways to do multidimensional scaling. I'm going to just describe one of them at first, and then we'll talk about other ways too. So imagine, first of all, I'm going to assume that because we have all these distances, obviously if you were in hyperdimensional space, you could plot these points all floating around in space, and we could achieve the same distances, but it wouldn't be like the map because we happen to know the Earth is kind of flattish, right? No, Dr. Gashler, it's round. Everybody knows that, right?
It's two-dimensional.
It's sort of two-dimensional-ish.
No, not sort of. It is two-dimensional.
Well, you're saying there are no mountains. There are mountains, but you're right. It's from LA to New York, there's going to be a change in elevation, but there's going to be a lot of change in latitude and longitude. So we're pretty safe ignoring elevation. In fact, let me put it this way, because this is a better way to do it in terms of principal component analysis. If we were to plot the eigenvalues, this is probably the eigenvalue of latitude, this is the eigenvalue of longitude, and this is the eigenvalue of elevation. This is the eigenvalue of what? Time? Or, okay. And because we live in a universe dominated by string theory where there are really 10 dimensions that we haven't even figured out how to measure yet, there's probably some other mysterious thing that can only be measured with quantum mechanics that nobody even comprehends or understands. But where LA and New York exist in the quantum plane is pretty much irrelevant to how far apart they are, right? Although it probably is relevant to some high precision. The gravitational wave thing that they measure at LIGO probably has to account for relativistic differences through time and space in the quantum dimensions and who knows what. But by and large, if we ignore everything but the first 2 dimensions and we measure the distance from Los Angeles to New York, or whatever 2 cities I had said last time, you're going to get it within a few inches and we'll call that right. Don't you agree? Okay, so do you understand this plot that I'm looking at here? I didn't actually describe this very well. Let's talk briefly about that. This is a plot of eigenvalues, or maybe it's root eigenvalues. I like to plot the square root of eigenvalues because eigenvalues are kind of a squared concept, and if you take the square root of them, then it's actually deviation rather than variance. What an eigenvalue is if you take your data and you say how much of the variance in this data is accounted for by the first principal component. That's the first eigenvalue. And if you say how much of the data is accounted for by the second principal component, that's the second eigenvalue, and so on and so forth. And if you add up all of the eigenvalues, you get the sum squared distance between all of the points in your data set and the centroid. Does that make sense? So the sum of the eigenvalues is the sum of the squared error of your data points. So here, let me draw some points. This is slow without a mouse. And the centroid is probably right there. I don't know why I always draw an X at the centroid, something to do. And the first principal component is probably, well, it's a vector starting at the centroid and pointing in one of those directions, right? And it doesn't matter which one. We'll say that one. So there's a vector emanating out from the centroid, which I'll reinforce. Okay. When we perform the Gram-Schmidt process in order to collapse the data onto the first principal component, we're removing some amount of variance from the data, right? If you measure the distance between every point in the centroid, you have the distance, you have a distance. If you take the squared distances and you sum them all up, that would be the sum squared difference between the points and that centroid. And that's a useful metric because it just comes up a lot in a lot of different types of analyses. The sum squared error, or sum squared difference from the centroid, is a way of measuring the variance in all of that data. Does that make sense? It's how much variance there is. Now, if these points happen to lie on a perfect plane, well, let's say all the points lie on a perfect line, then all of the variance is going to be accounted for by the first principal component. And when you subtract out that first principal component from it, all you're going to have left is a point, right? So then the first eigenvalue dominates all of the data, and thereafter you don't have much eigenvalueness. Now, if your data lies on a plane, then your first 2 eigenvalues are going to be big and the remaining ones are going to be small. And if you have a lot of big eigenvalues, that means your data occupies a lot of dimensions. So when the statisticians were inventing that personality test, they asked people a whole bunch of personality questions. What do you like? What's your favorite color? Do you like cats or dogs better? You know, et cetera. After they asked them a million questions, they performed principal component analysis. They took care to measure the eigenvalues as they were reducing the dimensionality. And then they looked at it, and it looked kind of like this. And when they saw something like this, they said, oh, look, it only takes 2 variables to account for what people are and who they are in their hearts of hearts and pretty much tell them all there is to know about their personalities. Therefore, we can reduce human beings to 2 dimensions and give them 4 colors, and we haven't lost much. And more specifically, this is exactly how much we've lost. Right? We can measure how much we've lost by reducing this to 2 dimensions. So yes, principal component analysis is lossy, but it's not this vague, we don't know how much is lost. That's exactly how much variance is not accounted for by the first 2 principal components. These blue dots represent your data set, right? Okay. This vector represents the first principal component. And we'll say this vector represents the second principal component. And you will have up to n principal components in your data, where n is the total number of dimensions in your data, right? Okay. If you were to fill a matrix with these vectors, we could say the first, we'll use rows, we could use columns if you prefer, it doesn't matter, because you can transpose a matrix. If this first row vector represents the first principal component in that data, and the second row vector represents the second principal component, and the third one represents the third principal component, we'll say this is four-dimensional data. This matrix of component vectors, each of these will be orthonormal basis vectors into which we could project the data. This matrix stores your principal components. The approach I taught you for computing principal component analysis doesn't go through a covariance matrix. Now, there are a lot of ways that people compute eigenvectors that involve first computing the covariance matrix. And the reason they do that is because it's a lot easier to teach in linear algebra form. It's a closed form of process. I'm more of an iterative process type of guy. I like regression. So I taught you principal component analysis is about regressing the line that fits the data. When you first compute the covariance matrix, then you compute the eigenvectors of the covariance matrix, and then you say those eigenvectors, the eigenvectors of the covariance matrix are the principal components of the data. That's the way it is often taught, and I'm kind of avoiding teaching that way. Now, suppose that we have your principal components, not your eigenvectors. Well, these are the eigenvectors of the covariance matrix. They're not the eigenvectors of your data.
Okay, that's
you see the difference?
my question.
I did, okay.
Because I was wondering.
Okay, so a covariance, let me just talk about that anyway, just because I'm betting not everyone in the class got that. Let us suppose this is your data, and your data is fat, meaning I'm going to use each row to represent a data point. Okay, so this is a single point of data in your data set, and it's also tall, meaning there's a lot of data points. If you compute the covariance matrix of this data, it will look kind of like this. It'll have the same number of dimensions as your data. Yeah, same number of features, but there will also be one row for each feature as well, not one row for each data point. This is kind of what your covariance matrix looks like. When you find the eigenvectors of this matrix, they will be the exact same size. So here's an eigenvector. Now, if you wanted, you could compute all d eigenvectors, where d is the dimensionality of your data. But usually we don't. We usually stop after we've found the first 3 or 4 of them. And this is one reason why nobody actually uses the covariance process no one actually goes through the covariance matrix to do principal component analysis in practice, because it's too darn expensive. You're going to compute the whole covariance matrix, which involves passing through your data d times. It makes the algorithm totally inefficient. Everybody uses an iterative process. The results, in theory, should be identical. There are numerical stability issues, and I'll bring that up in just a minute. But for the moment, let's say they're the same thing. Okay? Now, let's also suppose I have stopped early. And because I've used an iterative process, I have only done this much computation. I haven't done the full huge amount of computation necessary to compute a covariance matrix. Now that I've done this small amount of computation, I'm going to transpose this matrix and put it right there so that I can then multiply these together. This is my graphical way of multiplying, because now the dot product between this vector and this vector, for example, ends up being this element, right? You know how to do matrix multiply? Okay. Well, when I am multiplying each row in my data set by each principal component vector in my basis vectors, I'm projecting my data into the smaller number of dimensions, right? Because this first dot product, remember, each of these principal components are normalized vectors. And when you dot product with a normalized vector, you're saying, hey, project into that axis. And so this low dimensional vector is a projection of this big high dimensional vector into low dimensional space. In other words, it's a projection of this data point onto those three apparently orthogonal, orthonormal basis vectors. So when you code this up, you're going to see in the training phase, this basically means compute the first k principal components. And then the reducing phase, we're going to say for each row in your data, for each row x in your big matrix X, dot product it with the, let's see, is M? Yeah, M is the matrix of principal components. So when you dot product your point minus its centroid with the principal components, that computes y, which is a reduced dimensionality version of your original data point. Is that kind of mind-boggling, or is it sufficiently clear? To a large extent, all you're doing is you're taking the axes of your space and you're bending them to align with the variance of your data. And when you do that, those dimensions that have no variance left in them, you just kind of say, no variance in those, let's just throw them out. So another way of thinking about it is you're taking this data, this big high-dimensional data set, and you're kind of doing a linear transformation or a rotation of the axes to shift all of the data that you can as far into the, we'll say the left side, into as few dimensions as possible. And then what's left on the right side are just a whole bunch of zeros or numbers really, really close to zero. And at that point, we just throw them off because who cares? We're throwing off a bunch of tiny numbers that don't change much. And so now you have a small matrix. So we have reduced the dimensionality of this matrix by rotating the axes, by projecting, by dot products, however you want to say it, it's all the same thing. We're really just finding basis vectors that regress closely to the variance of the data, and we're using those as the new axes.